Thanks for coming to my session. As Justin said, my name is Lukonde Mwila. You can also call me Luke. And before I get into it, I just want to double check. Did everyone receive a non-disclosure agreement? It might be attached to the bottom of the seat. There's some confidential information I'll be sharing in this session. So I see someone shaking their head. Yeah, you're going to have to leave. I'm kidding. I'm kidding. All right, so this session is largely based on a project that I was a part of years ago. But to increase the value of what I'll be sharing, I did incorporate some newer developments in terms of security strategies or approaches that would be helpful to you if you're interested in this particular topic or you're dealing with challenges in this domain. Right, so if you want to connect with me, please feel free to do so via LinkedIn. Just use my full name. You can also subscribe to my YouTube channel if you're interested in Kubernetes or containers and cloud native related content. Also, the team that I'm a part of, the developer advocacy team that is, has a dedicated YouTube channel called Containers from the Couch, and we live stream a lot of cool sessions, usually have special guests on it, and I think you'd find that really interesting. Right, and just the last thing is I'm also a part of the SIG release team for 1.27 as part of the docs team. Great, so I don't know about you, but I love hearing people's stories regarding their first encounter with Kubernetes, the first project that they worked on. And I may be wrong, but I find that there are generally three camps, groups, or categories that people fall into. The first group are the people who are excited about the technology. Maybe they heard of it from somewhere, read an article, watched a video, or they've encountered or experienced its capabilities, and so they jump right into it. I'm going to liken Kubernetes to a destination. Maybe they buy the bus tickets to the land of K8s. And the second group are the people who don't really have a choice. You're walking, you're doing life, enjoying it, and next it's, hey, you're going to Kubernetes. Like, whoa, what is this about? Here's the ticket, this is the time, be there, right? The third group, which is the one that I fall into, there are a lot of question marks around this one. It's more of a conspiracy theory, but I believe the theory because I'm in that group. It's very similar to the second group. You don't remember any discussions. You don't remember a bus station or a bus ticket, as it were, but you woke up and you were surrounded by Kubernetes, a very different place. Now, thankfully, when this happened to me, I was part of a team, so we were equally new to this landscape that we were surrounded by, and we had been on previous adventures together, so we were ready to take this head on, eye of the tiger, bumping real loud in our minds. And then it didn't take us too long to find out that it wasn't going to be that simple. And for quite a while, we sold lies to each other, like this one saying, it's really easy. All you need to know is YAML, and you're 75% there with Kubernetes. Those of you that have experience with K8s would know that this is far from the truth. Anyhow, so we were tasked with migrating a microservice-based project from a previous container orchestrator to Kubernetes. And in this process, we were running stateless applications inside of our cluster environment, but a number of those applications needed to connect to databases outside of the cluster. And so we needed to find a way of storing our database credentials somewhere, as well as securely expose them for the applications to consume them in a safe way so that they can connect to the relevant databases. And so again, being new to the Kubernetes environment, sort of like being in a new town or a new building, you're taking everything in and trying to familiarize yourself with the place, and that's how we came across the concept of secrets in Kubernetes. And so secrets are one of two types of resources in Kubernetes that allow you to store configuration data. The other resource type is a config map. And if you take a look at their manifests, they're shaped in a very similar way in terms of their properties and the way they're structured in general. The main difference is obviously the fact that secrets are meant to store sensitive pieces of data, small pieces of information. And you can store things like database credentials, TLS certificates, etc. So this was a great find for us. And here's just a quick snapshot or a picture of a manifest for those of you that aren't really familiar with it. And like I said, a config map would look very similar as well. You'd have your key value pairs under the data property. Another main difference would be the type over there, because there are different types of secrets that you can create. So we went ahead, we created secrets manifests, and we're there talking to each other, excited about secrets, saying, all right, great, this has solved our problem. And then a new team member who is more experienced with Kubernetes joins the project, and this is essentially how it went down. Where they're like, hey, so yeah, we've got our secrets, we're going to store our database credentials in there. And he, spoke to us and said, okay, you do know that a fundamental flaw with secrets in K8 is the fact that the sensitive values are not encrypted. And then we had that Dwayne Johnson facial expression. Now, from that particular flaw, a number of issues are introduced. And so before we pulled our hair out completely, we thought, okay, let's take a step back. Now that we know this, let's try to understand how secrets work in Kubernetes in terms of the point of storage to the point of how they get consumed by pods. We'll start from there, and then we'll build on after that. And so this just kind of shows that flow. The secrets are stored in the etcd database, which by default, the data in there is not encrypted, including the secrets. And then you have the kubelet, which is an agent running on your nodes, and it will communicate with the etcd database through the API server. And it is going to the host will then create temporary file systems on the relevant nodes that actually have pods that need to access those secrets, and then the secrets are going to be mounted in there, and then you can consume the secrets using volumes and other approaches to expose your secrets using environment variables. So this was still good for us to understand that let's just see what the general life cycle is from point of storage to the point of consumption. Now that that's out the way, we can start panicking. So next thing to cover was essentially, okay, what are our primary risks and vulnerabilities that we are able to detect with secrets? And so the first one that we covered is the fact that the data in the etcd database is not encrypted, including the secrets. Another one is the fact that we wanted to store all of our Kubernetes configuration files, our resources, Helm charts in Git repositories. Unfortunately, because of this flaw with secrets, we couldn't keep our manifest files with those other Kubernetes resources. And then next we had to consider the process of how the secrets were going to get mounted. So sure, we could mount them as environment variables, but a challenge here is the fact that those environment variables are exposed to every single process running inside of the pod, and you could easily end up in a situation where if the system is being logged, you could have those secrets getting exposed. And so we're going to go the route of mounting our secrets as volumes, which is good. However, your secrets are then only as safe as your volumes. So that was another thing that we needed to think about. Okay, so we need to make sure that our volumes are going to be secure. And then a last primary concern was exploitation of the root user. Because the host, or the node that is responsible for actually creating and managing the file systems on a node, if someone was to gain access to the root user, they could easily exploit that particular vulnerability in order to gain access to the secrets in the temporary file systems. So this was good for us to understand so that we can have our moment of panicking, and then we switched from being excited about secrets to being more like Boromir here and saying, all right, now we are united in this fact that this is not going to be an easy process, but we have to figure something out. So how are we going to overcome these red flags? And one thing that I really like is to try and see if there's a way that you can bridge technical concepts or problems outside of the technical world and think through how you would solve some of those challenges, and then from there, translate that back to the technical space to develop your solution. And so we're kind of thinking, okay, secrets are not exclusive to Kubernetes, the concept of a secret in general. So let's think about how we would keep a secret safe, just in general. The best kept secrets are the ones that you've never heard of or have no clue about. Now, this is something that's a little bit tricky. We accepted the fact that there were going to be some measured risks that we would have to take along the way, and that will look different depending on your use case or context. This was happening at a financial institution, so there were some things that were just a non-starter for us. However, there were some areas where we were going to have to, quote unquote, bite the bullet and move forward with those particular measured risks. So we said, all right, so we need to work through these questions. Number one, what is the secret? That was a no-brainer. We knew what they were. It was our database credentials. Next thing, where is our secret going to be kept? Who needs to know about the secret? Or what parties need to know about the secret? How is the secret going to be shared? How will the relevant parties consume the secrets? How do you prevent the secret from being easily interpreted in the case that something should go wrong? And then lastly, how do you create additional guardrails or layers that will help you prevent exposure of your secrets? And so basically, we're going to work through these different questions over here, and the answer to each one we're going to translate to a technical solution. Some of them, as I mentioned, will have measured risks, but this is the approach we're going to take for our security strategy. So, first step is, where is the secret kept? And if you take a look at Bilbo over here, that's a reflection of where we were at. The secrets were up here in our heads. And we thought, well, we've been keeping them safe. Why should we change? I'm kidding. One of the main reasons we were dragging our feet a little bit about the storage was because we wanted it to fit within a GitOps strategy. And I'll get to that just now. But before we did that, there were insecure things that we were doing. This isn't being recorded, right? I'm kidding. There were some Slack calls, team calls, where these secrets were essentially just the values were being shared with the relevant people. You're creating manifests on the fly. And so we knew this wasn't the best approach, but we were moving slowly because we wanted to make sure that when we did land on something, it was going to fit within our GitOps strategy. And I just want to cover this briefly. I don't want to assume that everyone in the room is aware of GitOps. It's a paradigm or a model that brings together the concepts of Git and DevOps workflows. It allows you to essentially extend what you have with your application software, where you have a Git repository as the source of truth, and you can do the same thing with your infrastructure. It's not exclusive to the context of Kubernetes, but it works really well with Kubernetes because it's based on a declarative model. Kubernetes obviously supports both procedural and declarative approaches. And so using what is known as a GitOps operator, that tool would essentially automate the change control process for your infrastructure and your workloads to Kubernetes. The Git or Helm repositories become the source of truth or the desired state for your cluster, and the GitOps operator is going to continuously watch those sources and compare that to the live state and then reconcile that so that live state matches desired state. There are different tools like Argo CD, Flux, and Fleet. We were using Argo CD. Right, and so just to quickly cover the concept of applications with Argo CD. Again, this is just for additional context so that people are able to follow along. So in Argo CD, you have a custom resource known as an application, and an application essentially has a source and a destination. The source can either be a Git repository, a specific path in a Git repository. It can also be a Helm chart, and that will be the source or the desired state, and then the destination is a namespace on a particular cluster. And so we needed to find out how we were going to store secrets in a safe place and then have whatever solution we come up with fit within our GitOps strategy for our K8's resources. Now, we started to look a little bit closer about this whole concept of storing secrets in Git. And as I mentioned, the primary red flag or issue here is the fact that our secrets aren't encrypted. So if someone was to come across that particular manifest file, it's really easy to run a base64 decode command in order for them to get those values. Another issue is the fact that Git repositories are collaborative by nature. You have lots of people that get involved in these repositories. Some come, some go. But the point is they're meant to be shared. And in addition to that, you can't necessarily start applying fine-grained access control to particular folders or paths and specific constraining access to certain files, because that's not what a Git repository is meant to be. And then the last issue, and it's not really an issue per se, because commit history is great, but it's not so good if you're going to store secrets in there, because even if you delete that secret, someone could, quote unquote, go back in time, check out at a particular commit, and then be able to see the values from that secret manifest file. So instead of forcing Git to be something that it's not, we landed on just using a secrets manager, because that was going to allow us to meet the criteria for the security and policy criteria in our particular context. We would have our data encrypted at rest. In addition to that, it would expose an API for us to carry out the different lifecycle management operations for our secrets, including automatically rotating them. We would have that fine-grained access control. We would also be able to audit to see the use of the secrets and have additional visibility. So that was great when we landed on that particular situation. So we store our secrets in the secrets manager, and then once again we hit another blocker. And we're wondering, okay, the secrets are there, and the cluster is there. How do we get the secrets from there into the cluster? And so we came across a project which at the time was primarily being stewarded by GoDaddy. Now it's a CNCF project. I think it's still in Sandbox. And that is the external secrets operator. Just by show of hands, how many of you are familiar with the external secrets operator? Okay, there are a couple of people. So the external secrets operator extends the Kubernetes API and allows you to essentially fetch secrets from an external secrets manager and then pull the sensitive values and attach them to a new secret that it will create inside of your cluster's environment. So this is the approach that we were going to use. We're going to use the external secrets operator. And I want to go over some of the important resources in the general architecture of the external secrets operator. And the three that I want to focus on are the secret store, the external secret, and then the third one isn't highlighted there in the diagram. It is the cluster secret store. So I'll start off with the secret store. The secret store deals with how will we fetch the secrets from the external secrets manager. So basically dealing with authentication and authorization against the API where the secrets are actually stored. One approach is the one that is depicted in the diagram. I don't think this is the safe approach, but when you're just POCing it, it's a fast way to get going. You essentially can have your credentials stored inside of another secret, and so this was in an AWS environment, and so we had IAM credentials stored in a secret in the POC phase, and the secret store will then reference that particular secret in order for it to address the issue of how will we authenticate and have authorization carried out against the relevant API. The cluster secret store works the same way, except it has a global scope, so it can be accessed from different namespaces, whereas the secret store has is scopes to a single namespace. And then there is the external secret resource, which is another custom resource definition. So whereas the secret store deals with the how, external secret deals with the what. So what are we actually getting from the external secrets manager? So that is where you would define the secret that is being fetched and the values, the keys for the values that you actually want to get. But there are no sensitive values exposed in there. And once that process is carried out, the external secret will then create the final secret that will be created inside of your cluster's environment. This is called the target. That is something you also define inside of the external secret custom resource. Now, the approach that we followed, an alternative to having to create another secret, because that kind of takes you back to square one. It's like, okay, where are we going to store that secret? It's not exactly safe to have IAM credentials stored in a secret. We went with IAM roles for service accounts, which allowed us to have short-lived temporary tokens from an OIDC provider, and we could restrict that to a specific service account that the external secrets operator was going to use, so we didn't need to create another secret. That would just take us back to square one. So how did we apply this to GitOps? Well, the first step was that we were able to essentially refer to the Helm chart repository where external secrets operator lives, and from there, the external secrets operator would then be, let me actually go a step back, just keep it on this page while I'm still talking about this. The external secrets operator would then be deployed by Argo CD into our cluster's environment, and then the secret store and the external secret lived inside of our Git repositories. So this was the biggest measured risk that we took, because someone could still make the argument that you're still leaving breadcrumbs, because if an attacker or someone that shouldn't have access to any of our resources comes across those things, there's enough information to figure out, oh, okay, so even though there's nothing sensitive per se in the secret store, the external secret still had the names of the secret that is being fetched from our external secrets manager, as well as the keys for those particular values and the name of the target secret. So this is something that you'll have to think about. And just on a side note, a really cool project as well that you can have a look at is Bitnami Sealed Secrets, which allows you to encrypt your secrets manifest so that you can store them inside of a Git repository. For our context, that was going to be a non-starter, and I've heard other people who are in similar situations share the same thing, but it is still a really cool project if you actually want to just have the secret stored in the Git repository. You can have an encrypted form of that particular secret using Bitnami Sealed Secrets. Okay, so this was cool to some degree, but some of you might have already picked up on this. At the end of the day, external secrets operator still creates a secret that gets stored inside of our cluster's environment, and specifically in the etcd database. So to address this issue, we used KMS in order to encrypt, to add envelope encryption to our etcd database so that the secrets would also be encrypted at rest. So we've got our secrets in an external secrets manager. They're encrypted at rest over there. We use external secrets operator with a GitOps approach to deploy the relevant resources into our cluster's environment, which will automatically create the secret. And then that secret still gets stored in the etcd database, but then we had envelope encryption using KMS for the secret to be stored at rest. Right, so that's where we're going to keep our secrets. Next is who needs to know about the secret. And there are two particular areas that I want to focus on here, users and workloads. Now, this is where it was really helpful for us that we were using Argo CD, because there were application developers that needed visibility into the resources in the cluster's environment. There were solution architects, and there were also QA testers. The cool thing about using Argo CD is having the web server meant that users could essentially use the single sign-on approach with an external identity provider in order for them to gain access to Argo CD. And using Argo CD's role-based access control, they could just have visibility to the resources that are running the cluster's environment. They didn't need direct access to the cluster's API server. So they were restricted from that altogether. So with role-based access control, you can also restrict the applications that they have visibility to. And this essentially, as you can see with that arrow at the bottom over there, this is a good approach that you want to follow. Not everyone should have access to the API server, and so this worked out really well for us. But then we also have to think about how we're going to protect secrets from workloads. And here I want to cover namespaces, service accounts, and role-based access control. And so namespaces sometimes get a bad rep because by default, you still have traffic flow between pods that are in different namespaces. It's not strict isolation, unless you're going to implement network policies or have a service mesh for MTLS or authorization policies. However, they still provide a degree of isolation which is helpful so that you don't have pods in another namespace mounting secrets in another namespace. So it's still a good layer that you should have over there, and make sure that secrets are scoped to the relevant spaces. Now, the next thing is the service accounts. And service accounts are how workloads identify in the context of Kubernetes. And so we made sure that we made use of service accounts, of service accounts that were specific for that particular workload instead of using the default service account. And then from there, create a role that has the relevant permissions for that particular workload. And so in this process, you do have to think about what operations does this workload have to carry out against the clustered API server, if any at all. And then you can bind that particular role to the relevant service accounts. Now, if you don't define a service account, by default, Kubernetes is going to assign a workload to the default service account. And so you can also manage that particular process so that you disable the auto-mounting feature of service account tokens. I think from 1.24 that has now changed, but if you're running a version prior to that, then that is still something that will be carried out. And the reason why you want to prevent that particular thing is if you think back to the process of how the kubelet communicates with etcd through the API server and then mounts this into temporary file systems, if an attacker was to gain access to the root user, those secrets, the service account token is stored in a secret, and a root user would probably try and go for that particular token that is stored in that secret, and from there be able to communicate with your API server. So those are some good protection mechanisms that you can go with. This is just an example of a role and a role binding manifest. Again, some of you might be familiar with this, but for those that aren't, you can see over there, you can define the particular API groups, the resources, and what kinds of operations that you want your workloads to be able to carry out, and then bind that to a particular service. And also, as I mentioned, I'm not sure if I have a diagram for that. Let me see, it might be in the next one here. There we go, yeah. Is you want to manage what the default service account is actually able to do. So in the case that it's something that slips or falls under the radar, that you've already disabled the auto-mount service account token feature so that you're protected in that particular regard. And then a cool exercise that you can just carry out is running the kubectl auth can I command. Some of you might already be familiar with this, and you can essentially run that against a particular service account to see what operations it's able to carry out. And so you can see right at the top over there, I'm checking if this service account can get any secrets, or if it can. The second one is to see if it can list any secrets, and third is to check if it can watch any particular secrets. So you can carry out an exercise like this to make sure that your service accounts have a least privilege principle and see whether or not they even have access to the secrets API in Kubernetes. Okay, next up is how is the secret shared and how is it going to be consumed? I've already covered this in part with when I discussed the GitOps workflow. So that was the foundational flow for how our secrets are going to be shared into the cluster's environment, as you can see over here. And as I mentioned, Argo CD is watching the Helm chart repository for the external secrets operator in order for it to deploy it into our cluster's environment. And then we had our secret store and the external secret running inside of our Git repositories, which were then being deployed. And as I already mentioned, that's how the secret would get created and then can eventually be consumed by the pod. Right, so next I'm going to cover consuming the secret. And you heard me mention earlier on that we decided on going the approach of consuming the secrets as volumes, but then our secrets are only as safe as our volumes. And so we were able to then encrypt our particular volumes using KMS, and this was how we addressed that particular layer as well. So mounting them as volumes and then encrypting the actual volumes for those particular instances. And then lastly is, how do we prevent violations that risk secret exposure? And so this is essentially just what are the additional guardrails to prevent an application, workload, or the wrong kind of role ever being created to begin with. And so this is where admission controllers can be really helpful. And here I'm demonstrating with OPA Gatekeeper, and I'll show you that shortly in a walkthrough. And admission controllers essentially intercept the API requests to the API server after there's already been authentication and authorization, but before there's been any persistence to the etcd data store. And so you can use a tool like OPA Gatekeeper to essentially put guardrails in place, and the ones that I'll show you in a short moment are to prevent secrets from ever being mounted as environment variables. And so in the case that someone committed a deployment like that into your Git repository, or if someone tried to run a kubectl command, then your OPA Gatekeeper would essentially prevent that from running. And in the case that that was running before that guardrail was in place, you would be able to detect the violation with OPA Gatekeeper. And then another example that I will also show you is for roles. You can also create another guardrail to prevent roles from ever being created if they are going to have secrets operations. So that's another approach that you could use. Great, so lastly, I'm gonna show you this in action. But first, I just wanna walk through the code. If you could just confirm if it's big enough, someone right at the back, if it's clear and visible. Oh, great. Cool, so I'm gonna walk through some of the resources that I did discuss. So the first one here is the external secret, just so you can see what it actually looks like. Scope to a particular namespace, and here's the name of the external secret. You can also apply your refresh interval. So over here, I set it to 240 hours, because when I was working on this last week, I was like, okay, I don't want anything weird happening before the session, so I'm just gonna make sure it only refreshes after KCD LA. I had a funny incident once where a session token, I think this was for GitHub though, expired the day before a conference that I was speaking at for a demo. And so it was in the middle of the night, and I'm just gonna go through this demo all over again just to see if this is still working, and it was failing in the CI stage. So thankfully I was able to pick that up. So I try not to take chances. Anyway, that was a side story. So you can see over here, this is where we refer to our secret store, and I'll show you that in a moment. And you can see over here, the kind obviously is a secret store. Remember that there are also cluster secret stores. That's the name of our secret store. And then the target over here, this is the secret that external secrets is going to create that will be running in your cluster. And under the data, over here, you'll see value, one which is actually referring to the key that lives, the key for the secret that is stored inside of your external secret manager. And the same thing over here, value 2 is that's what it's referring to. And then you can see under remote ref, the key over here, this is the name this is the name of the secrets, and then the property is value1. And so then this is then going to be added to the secret that is going to be created inside of your cluster's environment. Next over here, you'll see the secret store. And what I want to draw your attention to, you can see under here the provider using AWS and the services secrets manager, define the specific region. You can see auth JWT, and then the service account reference is express Node.js SA, which is this one over here. If you recall, I mentioned we were using IAM roles for service accounts. And so here's the particular annotation for the role that had a policy attached to it that allowed for those permissions in order for us to communicate with secrets manager. This is a safer approach than having to create a secret with IAM credentials that's going to live inside of your cluster. This is something that I already showed during the slides. That's just the disabling of the auto-mount service account token feature. And then just what I want to go through briefly here, I know that it can be a little tricky to get into the details of working with OPA Gatekeeper, so I'm just going to focus on what's taking place. And so you can create your constraints, which are essentially like your guardrails, and you can create constraint templates from which those constraints will be created. And inside your constraint templates is where you would essentially be defining a custom resource definition, which will be the constraint that gets created. And you can also use a policy language, which I'm scrolling down to over here, called Rego, in order to create the relevant functions for your the particular constraints that you're going to be creating. And so this one here is, just head straight to the description, controls the ability of any pod to mount a secret as an environment variable. And so that's what this function is dealing with over here. It essentially checks the containers that are being created in a particular deployment or pod spec, and then looks to see if any secrets are being mounted as environment variables, in which case if it detects that, then it will that will be detected as a violation. If this is being created after the constraint has already been deployed to your cluster, then it will prevent them from running at all. Otherwise, it will detect them as violations. And then over here is another type of constraint, and what this one is doing is checking to see if there is a role. So you can see over here, check if resource is a role, and then checking to see if there are any rules that allow for any operations against secrets, because that is something that you also want to prevent. As I mentioned, I'm glossing over this. I don't want to assume that everyone is familiar with Rego or with OPA Gatekeeper, and that would be a deep dive in and of itself. I just want to focus on the solution and how that can help in your particular context. So, I think I accidentally just closed the file. Anyway, so I'll focus on this one over here. So this is a role that I believe, oh, this is the constraint actually. So let me go to disallowed role, that's right. So here's a role, and you can see under resources, we've got secrets over there. So this is something that we want to prevent, right? And so I'm going to now show you Argo CD. And you can see that it's currently out of sync. There's something that has gone wrong. And if I click on the error over here, you'll see that it failed to sync, object failed to apply, and the reason is admission webhook denied the request. And this is basically you can see their roles should not have get, list, or watch permissions for secrets. So this is just to show you how you can essentially protect your environment. It's one particular approach, and that's the specific role over there that was an attempted creation of a role that was violating one of the protection mechanisms for our secrets. All right, so that's it, and we can move into some time of Q&A.
Let's get those questions. And the mic's gonna go. Test, test. There we go.
Great chat.
Thanks.
You said that sealed secrets were a non-starter. Can you elaborate on that?
Right, so in our context, Bitnami sealed secrets were a non-starter. Having a conversation with an internal security team at a financial institution that a secret is encrypted, but it's going to be right there in a Git repository, they took a long, hard look at us like, So it's right there, you know. And now look, in some contexts, that's a measured risk that would be approved. In other contexts, the measured risk that we took might not be allowed in terms of that external secret, because that still leaves some breadcrumbs, you know. So, but I love Bitnami sealed secrets, and I still advocate for it. I think it's an excellent resource.
Other questions?
Can you talk a bit more about KMS?
Sorry?
Can you talk about KMS?
KMS.
Yeah.
Right, yeah. So KMS, and Justin, you can piggyback off this one here, essentially allows you to apply encryption with a specific key. You can use, Kubernetes also has a KMS feature. I think it's still in a beta state, if I'm correct. KMS with Kubernetes. I think it's still in a beta state, but you can also use cloud providers, so that's the approach that we used, essentially generating a key so that you can encrypt different resources. It's not actually exclusive to Kubernetes resources, but it's great that you can extend it to that. Yeah, but I can also share some resources with you to delve deeper into that. Sure.
So this is a follow-up to that. I saw that you could enable the encryption of etcd itself in the EKS on AWS. But if you have to encrypt the volume, how do you do that? You have to write something for doing it, or is also something?
Right, yeah, so that's something I can, great. I can actually share the docs with you as well about how to do EBS encryption, volume encryption. And just to be clear, so EKS has default encryption of the EBS volumes for the etcd nodes, but you obviously don't have visibility of that. But then you can add envelope encryption with KMS for the etcd data stores. But I can share some docs with you for encryption for EBS volumes for instances that you would obviously have visibility and control over.
Hello, great job. One of the questions around exposing secrets at a namespace level, you talked about assigning at a namespace level. What if you have a set of applications within a namespace that may have different secret requirements? At that point, do you enforce that through an RBAC? Like if you have multiple secrets for...
Oh, multiple secrets in the same namespace.
Correct.
Right, yeah, so at that point, I would probably consider using an admission controller for finer-grained custom access, like custom policies to ensure that specific workloads in that namespace can't access a certain secret in that namespace. So obviously it's a little bit more complex, but definitely worth it because you want to have fine-grained thing as well. You don't want application A, just because it's running in the same namespace as application B, ever having access to, ever having the chance to mount a secret that belongs to application B. So I think custom policies can be really helpful in that scenario.
It sounds like you looked at a lot of different solutions. Did you look at Vault, and why did you throw that out, or did you get around to it?
Sorry, please repeat that.
HashiCorp Vault.
Oh, what do I think about it in general?
Did you look
or?
at it or try that compared to the other solutions?
Oh, right. So we did look at it, but at the time there was biases for certain tools. I mean, just to begin with, as I shared with the story, we woke up in the land of K's. There was no discussion. So there were some things where we had to deal with certain scenarios where it was like, hey, you don't really have a choice with certain tools. But I think HashiCorp Vault is an excellent one as well. So no issues with Vault per se.
So I'm going to apologize if I missed this.
Sure.
But you talked about having policies to make sure that secrets were not mounted as environment variables.
Yes.
Now I do this a lot. Why would we not mount secrets as environment variables?
Yeah, sure. So it's something that I actually did cover.
I apologize over that little.
No, that's fine. That's totally fine. Yeah. So when you're mounting secrets as environment variables, they're exposed to every process running inside of the pod, and also because of systems typically being logged, they can easily be exposed in that particular sense. With volumes, it allows you to be a little bit more selective about the container accessing a specific file path where the secret is going to be stored.
Depending on how large your secrets and environment is, there is a limit on the environment the process can have itself, a Linux limit. So just another thing to maybe look out for.
And just to be clear, even though I'm sort of advocating for the approach with volumes, if you have a lot of them, it starts to get a little complex. So just still do your due diligence with what that will look like in the long run.
As far as access to secrets, is there a way to prevent people from execing into a container from being able to see the secrets?
Right, yeah. Thank you. That's something I was actually supposed to mention. So that actually goes back to the topic of sharing secrets and with your users. So with operators, you can actually, that's where you could also this is assuming you go with an approach that we took, where with application developers, they were never even going to communicate with the API server. And sure, they can see the secret on Argo CD, but it masks the value, so they wouldn't be able to even get the base64 encoded version. Right. Right, yeah, thanks. Oh, if they have permission. Yeah, I'm not too sure. I'm not too sure about that one. Yeah, no, I don't want to lie to you. That one I'm not too sure. So I'd just advise more for a strict approach, where if someone shouldn't have access to a particular pod at all, then you could define that. Yeah, but
You would
Justin?
probably handle that with a different layer, something that has runtime security like Falco would alert for those sorts of things, or SE Linux or something else can probably do that, but it's going to be really complex. What has what does the shell have access to versus the process? And so restrict shell, yeah, but or use another wrapper around shells. And there's other things that can let you access better logs in like Pocket containers, a sidecar container to bring in for debug. Those you can probably restrict it a little differently.
Cool.
Did you have any requirements for how to rotate secrets? Like how often you would rotate them? Was there a TTL, and how would you handle that?
Yeah, and so you might have seen with the external secret resource that there was that refresh policy. So that's something that's going to vary, but it's definitely advisable for you to be changing those values often. And often, again, is going to be subjective depending on the context. In some cases, it might be, yeah, so. Yeah, so that in that particular sense, it would vary, but definitely there should be automated rotation taking place. You don't want to have unnecessarily long-lived. And again, unnecessarily long-lived is subjective. So.
Do you have a way to recycle the secret if it's been updated and you have to do an emergency, reset or something like that? You don't want to wait for the refresh interval.
Oh, I see. With external secrets in particular, that's actually a really good question. I think we might have actually run into that issue at some point. And I think we did a MacGyver approach, to just delete the resource, and then Argo CD then obviously just does its process, yeah, of redeploying it. But that might actually be something that they address now. With Argo, right? Is that with the Argo CD with the, okay.
All right, if there's no more questions, thank you so much for coming. There is a 15-minute break, so come back in here in just a little bit. And thank you, Luke.
Yeah, thanks.